Hi everyone, in this lesson we're talking about estimating limits when you're given a table of values for a function. So we're going to start by considering this function, f of x here, and this is a rational function because it is a ratio of a linear polynomial in the numerator and a quadratic polynomial in the denominator. And what we want to do is we want to find the following limit as x is approaching -3. And to begin, I'm going to present you with a table of values for the function. So whenever we plug in x equals -4, we get as the output of the function -0.2. Right, so where it says where it says x on the first row of this table, this is the input to the function. What we're going to plug in for x here, like we'll let x equals -4, for example, to get the output, which we're going to list in this row, the bottom row of the table. Then, if we plug in -3.1 for x, the output becomes -0.2439. And when we plug in -3.01, it becomes, as an output of the function, -0.2493. And then finally, with -3.001, we get the output -0.2499. And so I just want to illustrate this on a number line. So let's say this number line represents x, which is my input to the function. If we have -3 represented by that line and -4 represented by that line, what we've been doing on the top row here for the input to the function is we started off at -4, and then we did -3.1, and then -3.01, which is maybe right here, and then -3.001, which is almost right on top of -3. So what we've been doing is we've been approaching x equals -3 from the left. And as we're approaching from the left, we're kind of taking a left-sided limit. So what we need to do is we need to look at what value in the output of the function are we approaching as the input of the function approaches -3. So as we're getting really, really close to -3, it looks to me like the output of the function is approaching maybe -1/4. So we're approaching -0.25 as we get closer and closer to -3 in the input. And so when we want to find this limit here, the limit as x approaches -3, a good guess based on looking at this table would be to say that it was -0.25. Okay, yeah, so down here when the question asks what is the left-sided limit at x equals -3, we're talking about -0.25. Okay, so here's another table with values of the same function, but this time we're starting at x equals -2, and so let me draw another number line just to make this clear. Here's my values of x. If I start at -2 and here's -3, what we're doing in this first row with the inputs to the function is I'm starting at -2, and then I go to -2.9, which is like here, -2.99 and 2.999, and I'm getting closer and closer to eventually -3. And what's happening in the output of my function is I'm going from -1/3 to -0.2564, -0.2506, -0.2501, and again, it looks like what I'm approaching as I approach -3 in the input, it looks like the output values of my function seem to be approaching -0.25. And as I'm coming in from the right, I'm coming in from -2 as I approach -3. It seems like I'm taking a right-sided limit. And so for this question, it looks like the right-sided limit here is -0.25. And so it asks, does the two-sided limit of this function exist at x equals -3? And I would say yeah, because the left-sided limit exists, the right-sided limit exists, and they are equal to each other. So I'll say yes here. And then lastly, we say, is the function defined at x equals -3? We take a look at my function. And we ask, is this guy defined when x is equal to -3? Well, let's find out what would be the value of this function if I take f of -3. Well, in the numerator, I have -3 plus 3, and in the denominator, I would have -3 squared plus 2 times -3 minus 3. So this is 0 in the numerator, and then -3 squared is 9, plus 2 times -3 is -6 minus 3. So it gives me 0 over 0, which is not a real number. So actually, here at x equals -3, the function is not defined. And what type of discontinuity exists? Whenever the two-sided limit exists, but the function is undefined there, that type of discontinuity we've learned in previous lessons is a point discontinuity. Because if it were a jump discontinuity, or an essential discontinuity, or an oscillating discontinuity, you wouldn't have the two-sided limit exist as a real number. Okay, so now we want to look at the following function again. And it's actually the same function as before, so that should look familiar to you. But this time we want to find the limit as x approaches 1. And to do this, we're going to look at this, this little table right here. And what I'm doing is in the x values, or in the input values, I'm going from 0 and approaching 1, right? So I'm going from 0 to 0.9 to 0.99 to 0.999. And in the output of the function, we're going to look and see what happens as I get closer and closer to x equals 1. So in the input, we approach x equals 1, and it seems like we're approaching x equals 1 from the left. And my output values are going -1, -10, -100, -1000, and in fact, it seems like these are kind of approaching negative infinity because they're just getting larger and larger at a faster and faster rate, right? And so it seems like when I approach x equals 1 from the left, I'm approaching negative infinity. So when this question asks, what is the left-sided limit of our function at x equals 1, I would say that the limit as x approaches 1 from the left side of my function is negative infinity. Okay, same function, a table with more values of our function. Let's see what we have. So as my inputs are going from 2 and getting closer and closer to 1, it looks like I'm approaching x equals 1 from the right side, right? Because I'm coming in from 2 and going towards 1. And the output values of my function are going 1, 10, 100, 1000. It looks like I'm approaching positive infinity because these numbers just keep getting larger and larger. Now, that means if you asked me what is the right-sided limit, as x approaches 1 from the right side of our function, to me this looks like positive infinity based on our table. So when we ask the question, does the two-sided limit exist? Well, my left-sided limit exists at negative infinity, and my right-sided limit exists at positive infinity. That means my two-sided limit does not exist because both of my one-sided limits, they give me different answers. Is the function defined at x equals 1? Well, we can try it. We just have to plug in x equals 1 and see what we get. And so taking this function at x equals 1, I get 1 plus 3 in the numerator. That looks good so far. And then the denominator, we have 1 squared plus 2 times 1 minus 3. So in the numerator, 4 over 1 plus 2 minus 3 is 4 over 0. And so the answer is no, because 4 divided by 0 is not a real number. So our function isn't defined here. And now, what is the type of discontinuity? Well, on one side, on the right side, my limit is approaching positive infinity. On the other, on the left side, my limit is approaching negative infinity. This seems like it would be like a essential discontinuity here, right? So it have a little vertical asymptote. Right here along x equals 1. So on the right side we're going up to positive infinity, on the left side it looks like we're going down to negative infinity. Okay, let's look at another function now, just a new example. And let's take the limit as x is approaching negative 5. First we're going to look at this table of values. And so as my input values go from negative 6 and we approach negative 5, from the left side, going from negative 6 up to negative 5, let's see what happens with my output values. Well, every one of those output values is negative 3, so I think it's fair to say that we approach negative 3. In other words, the limit as x approaches negative 5 from the left side of this function is negative 3. It's my left-sided limit. Looking at another table of values that I created from the same function, my input values are going down from negative 4 to negative 5, so I'm approaching negative 5 from the right side here. My output values seem to be stuck at positive 3. So I would write that my right-sided limit, or the limit as x approaches negative 5 from the right side of my function f of x, is positive 3. Now we can ask, does the two-sided limit exist when x is negative 5? And the answer is no, because even though I have both the left-sided and right-sided limit, they give me different answers. Is the function defined at x equals negative 5? Well, we can try it. We can go back to my original function and try what is f when x is equal to negative 5. This would be 3 times negative 5 plus 15 in the numerator, and then the denominator I have absolute value of negative 5 plus 5. And so this is going to be negative 15 plus 15 over absolute value of 0, or in other words, 0 over 0. And 0 over 0 is not a real number, and so I say my function is not defined here. If not, what is the type of discontinuity? Well, this seems to be a jump discontinuity, because on the right side, all of my values seem to be positive 3, and on the left side, all of my values seem to be negative 3. And it just changes suddenly right at that point, x equals negative 5. And now this is our favorite function, the very, very weird oscillating discontinuity that we've seen in previous lessons. And again, we won't deal too much with trig functions in business calculus, and so I won't dwell too much on this, but I just want to show you that if I made sort of similar tables representing the right-sided limit, representing the left-sided limit, and the right-sided limit, so as I'm approaching x equals 0 from the left side and the right side, I want you to notice that these output values, they don't follow any kind of discernible pattern. They don't seem to be approaching anything, right? These values are just, they seem random. And since they're not really approaching anything, we say that actually the right-sided limit does not appear to exist. We say the left-sided limit does not exist, and so then the two-sided limit does not exist. And of course this was an oscillating discontinuity. Again, don't worry too much about this one, because we're not going to deal a whole lot with trig the rest of the semester. You won't see too much sines and cosines, in other words.